Welcome to the chapter on groundwater. A few weird slides first. This is an interesting slide showing from 1990 to 2010, a span of 20 years, the ice frozen on the poles on Earth. Thanks to satellite technology, we can quantify this. Notice that from 1990, what is this, 91, 92, 93, 92 to 93, it increased. Ever since then, on the general, it's been decreasing. We are down over 1,000 gigatons of ice. Here's just a cool slide. I used to live in Athens. Here's one of the theaters in Athens, and they're showing the wonderful movie Silence of the Labs. And last chapter we were talking about rivers and how when a river reaches its base level, it slows down and drops its load. Well, here's an artificial base level created by a dam, a little place called Dilkon or Sibadalkai, northeast of Winslow, northeast of Winslow. And here, where the river has slowed down and dropped its load, it has completely filled up the dam, including with a tire. Below the dam, almost like a plunge pool, it has scrubbed out the bedrock. Now groundwater. Here's what you're going to cover in this chapter. You're going to compare the amounts of salt and fresh water on Earth. You're going to describe the movement of water in the water cycle, although we've already done that, so I don't know that we're going to cover it much more. We'll define the water budget for Arizona. We'll identify and describe factors that determine how much rain becomes groundwater. We will list factors that determine the amount of pore space in rock. We'll give examples of the difference between porosity and permeability. We will draw a typical water table. We'll list factors that and affect the depth of the water table. We'll compare and contrast wells and springs. And I think we're going to cover these enough, so I don't need to talk about them anymore. That was enough. Here's your typical water table. You'll remember this. Evaporation, condensation back into little teeny droplets that are so light they stay up in the air, precipitation, runoff, evaporation, transpiration, and what we're talking about today, groundwater, where this water infiltrates the pores of the earth. Pie charts are good. Here's an example of a pie chart. But we need something better for groundwater. This is kind of a cool little graph. This is where Arizona overall gets its water. The Central Arizona Project, which brings water from the Colorado River at a cost of billions of dollars over to Phoenix and now to Tucson, is 24% of our water. Using water right along the Colorado River, 18%. The salt and the verde, 8%. We actually use waste and recycle it, 3%. The Gila, the Little Colorado River, and a few others, 8%. And the biggest portion of it, 39% of our water. What you drink, what you bathe, what you use in your yard, what we water the golf courses with in the desert comes from groundwater. We're taking out a resource faster than it's being put back. That's an issue. Where does most of the water go? Well, most of it goes to agriculture. No surprise, growing things in the desert uses a lot. So this groundwater is being used up so we can primarily grow, well, a lot of this is feed for cattle, believe it or not. Municipal and industrial, that means houses and cities use about a quarter of it, and then industry uses about 6% of that. This is a cool little graph. How much groundwater do each of the major cities or areas in Arizona use? In 1985, 6% of the groundwater, or the water in Phoenix, came from groundwater. Since that time, it has dropped to 23%. Why? This thing, the Central Arizona Project. The canal coming from California across northern Arizona, or the northern part of the Phoenix area. You see it north of Bell Road. Offsets a lot of that. Tucson, up until the early 90s, relied completely on groundwater. Now it's down to about 53% of its water coming from groundwater. We'll talk about this later in the lecture. Where's Earth's water coming from? Well, most of the water on Earth, as you already know, no, you don't. That came from Chapter 1, and most of you guys didn't do that. Most of the water on Earth is saline, or ocean water, 97% of it. Only 3% of it is non-salty or fresh water. Out of that 3%, over 2/3 of it are frozen in ice caps and glaciers, although as I showed you in a previous slide, that amount is going down. Groundwater is where most of the non-frozen, non-salty water is, almost 1/3 of that. And then We have surface water and something else called connate water, which I passed in the very beginning. Water trapped in the rock, but isn't really groundwater. Um, Out of the surface water, this is where it is: lakes, swamps, rivers. This is a real cool graph for those who are into hydrology about where the water comes from and where it goes. I don't know if this is real big to use, but in general, irrigation of livestock and, believe it or not, generating electricity use a lot of our water. The nuclear power plants, the coal power plants that need to be cooled, they evaporate a lot of water. But again, according to the water cycle, any water that is evaporated, where'd I go? I lost it. Any water that's evaporated does go back into the water cycle, so we don't really worry about that too much. Industrial mining, and then here's where you and I are: schools, houses, city uses. A couple of concepts. Porosity. When you see a river running down its bed or its channel, in Arizona, very often this water will disappear. It's not disappearing due to evaporation. It is actually soaking down into the ground, into the little particles. If you could zoom in like some science fiction movie, well, people have done this, you could go down into the little pores between these particles or sand grains. Here's a typical experiment I would do in a science class. You take a soil sifter, and you can sift out gravel, sand, silt, and clay. You then take those materials and you put them into graduated cylinders, and you find out something interesting. Gravel has a lot of pores, clay has a lot of pores, but because they're not interconnected, it's not very permeable. Here's some good data. Gravel, 20 to 40% porosity. Sand, 30 to 50% porosity. Clay, it has this much porosity, but notice the pores are so small that water can't get through clay very well. Water can get through gravel and sand very well. It cannot get through silt too well. If you want to compare this to rocks, conglomerate makes an excellent aquifer or rock through which water can travel. Sandstone can be good too, unless it's poorly sorted or it has a lot of cement between the grains. Shale or slate is very poor to pore. So is crystalline rock like granite. Volcanic rock, boy, it varies. Here's what we're talking about. If you have little particles and they're angular, the angles, once they're vibrated, fit into the cracks of the other particles, and you end up with a lot less pore space. If they're rounded, you get more pore space. If you end up with mixed materials, poorly sorted we call it, you end up with little pore space. And this would be low permeability too, as with this. And here we'd have high permeability and high porosity because these particles are well sorted. The type of thing you find in a consistently flowing stream. Now let's talk about the water table. When the water hits the surface of the earth in the water cycle, some of it, as you know, will soak down into the ground. It'll soak down until it hits an impermeable layer, a layer that water can't get through, and it begins to stack up. The top of this we call the water table. Now where the water table intersects the land, you will have either a lake or a stream. Sometimes the streams will be contributing to the water table. Other times the water table will be causing the stream. In Arizona, a lot of times our water tables drop on either side of our rivers because our rivers aren't permanent. Here's what a well is. It's just a hole we make to go down to the water table. You could dig a hole, tie a rope to your brother's leg, drop him down here with a bucket, and have him pull it up. We used to do something like that in the old days. Okay, maybe not the brother idea, but you get the idea. Here's another weird thing. This is a little layer of shale underneath the ground, and it's stopping the water from going down. So we end up with something called an aquifer. This is an aquifer. Any storage of water underground is called an aquifer, like aqua, water. The water stacks on top of here, and when it hits the surface of the earth, it will come out in what's called a spring. Not a boing boing spring, but kind of like a leak in the earth, like this. This is Roaring Springs on the north rim of the Grand Canyon, and it really does roar. Why is it here? This is a layer of shale right underneath here. The water is stacking up behind this cliff and it can't get through the shale. So it's forced its way out through this sandstone or limestone. I can't remember which one. I did try to spend the night here once when I was working on the Grand Canyon, and this was a bad idea. It really is roaring. Here's another picture of what goes on. Here's the water table. Now let's add a couple of names. Anywhere beneath the water table is called the zone of saturation. Anywhere on top of the water table is called the zone of aeration. Right along the water table, if you look very closely, there's a little area where the particles are coated with water, but they're actually above the water table. This is called the capillary fringe. If you were to build an underground house and you built it down here, well, you'd need scuba equipment. If you built an underground house in here, you would just see water dripping through on occasion. Now here's some fancy terms. Vados, a word I used in Scrabble recently. And here are how lakes and streams form. Saturated rock contributes its water to those water features. Okay, let's talk about gaining streams and losing streams and dry stream beds. When you have a lot of water coming into an area, it will contribute to the stream. This is what I was talking about earlier. In this case, the water table is higher than the stream. Here's a typical Arizona river where we have water going down a river and more water is soaking in than is being contributed to the river by the aquifer. This is a losing stream. And when the river dries up completely, you still have water beneath it, which is why in the old Western movies you see people digging down in the stream beds, or you even see animals digging down in the stream beds, like in Africa. They know what's going on. They can smell this. Wells. What we talked about earlier was a normal well, but here's an interesting situation. Let's say you have a layer of impermeable rock, shale or slate, another layer of impermeable rock, and between them sandwiched is sandstone. If you have a rainstorm up here in the mountains, the rain's going to fall on all this, and some of it's going to go down in the sandstone where it'll be trapped. If that water stacks up, stacks up, stacks up until it gets to this level, there's where your hydrostatic pressure is. If you go down here and drill, you don't need to pump this water out because the level of the water is really higher than your well. We used to have a lot of these in the Midwest. However, since we've drained most of the water from these things out, we have very few aquifers left in the United States anymore that are artesian wells. We'll pause here and pick it up in part 2.